Good afternoon, everybody. Mr. Armke back with you again for CTS-120. Let's take a look at Chapter 4 today. So Chapter 4 is all about troubleshooting computers and supporting the power system. So our objectives for today are to describe the methods and devices that we use to keep a system cool, because of course power generation results in waste heat. We're going to look at a power supply selection method that allows us to meet the needs of a system comfortably. We're going to demonstrate an organized approach to solving any computer problem, especially hardware problems during the boot, and troubleshoot problems with the electrical system, motherboard, processor, and RAM. Now, if the CPU, motherboard, RAM, other components start to overheat, the system can become unstable. If this instability is sustained for a long enough period, or if the heat damage is severe enough, components can either fail or become damaged. Now, our general rules to keep the inside of a case cool is to keep the case closed, keep it clean, and make sure that it's in a location that provides good heat expression. So here we have in the left-hand side a figure of a passive or fanless cooler. Now this could be used for a fairly low-end system. This would be something that would use the copper pipes that you see there to contain a volatile liquid that would cause evaporation and condensation radiating throughout the fins of the cooler radiator system above it. So, CPUs often have heat sinks that are block-based that have these types of fins, but they usually will also have a fan, create what's called a cooler assembly. And then you will sometimes also see what's called a liquid cooling system, which I'm sure you've heard of, which instead of using air and radiant metals, will instead use a coolant, something not too far off from the antifreeze that you put in your car, in order to radiate heat more efficiently. Computer systems are designed to keep processors below a particular maximum temperature. A good cooler should maintain a temperature of about 90 to 110 degrees Fahrenheit or 32 to 43 degrees Celsius or centigrade. The cooler assembly is, as I said, the combination of a fan, a heat sink, and then any other accoutrement that may be included. In some cases, people will include the thermal paste because it's an enhancement. Some people won't. Because they often come pre-applied, I do list it in here as part of that, but it's really just kind of a matter of semantics. The heat sink uses its fins and increased surface area because of the very thin air spaces in between each individual metal fin to draw heat away from the processor and radiate it out into the air. The greater the amount of surface area, the more fins, the more space exposed to the air, the faster the heat will radiate and reach equilibrium. The fan enhances this by blowing the drawn heat away from the CPU unit and pulling cooler air from the bottom into the fins. The heatsink is usually made out of aluminum, copper, or some combination of both. There will sometimes be alloying or composite materials that will provide a better thermal response. The cooler assembly is bracketed to the motherboard using a wire or plastic clip. Sometimes they'll be screwed into place, especially with the Wraith style tower coolers for the new AMDs, the Ryzens. And then we place a thermal compound in between the bottom of the heatsink and the top of the processor in order to eliminate air pockets and enhance the convection of heat away from the CPU. This fan assembly is going to get power by drawing a 4-pin fan header on the motherboard. There will also be additional connectors for fans for optional connectors of additional case fans. Like my particular tower fan that I use at home has 3 fan slots on the back, 3 fan slots on the top, and 1 fan slot on the front. But the one on the front is a fairly large one. I can't remember if it's 140 or 160 millimeters, but it's pretty big. And the speed of those fans, the controllers that regulate them, and sometimes they're illuminated in order to have like red, green, and blue combinations of color effects. So fans have become not only a functional thing, but a decorative one as well. So here we have a very simple processor cooler. It's just a heat sink and a fan assembly mounted together. You can see that the blades are curved and that the bowl of the heat sink is also curved to kind of match that. This is what we call cowling, the spacing between a fan and its exterior container to prevent the blades from contacting other items. The tighter the space between the cowling of the fins and the edges of the blades themselves, the more generation of downforce is able to be provided by the fan, or upforce depending on the direction of flow. So usually designers will leave a minimum of space there just for tolerances and things like that, because these are mass produced, but they'll be pretty tight comparatively. You can get a piece of paper or the end of a pen in there, but you're not going to be able to get a finger in between for the most part, except for, as you can see, the spaces where the clips will move, because usually that requires a little bit more work. The best heat sinks are usually billeted out of a single piece of aluminum, which means that they're carved. Unfortunately, the cost involved is pretty exorbitant, so the easier way to go about that instead is to take an aluminum base block and then weld the additional fins on top in an arrangement that's similar to what we see on the right hand side here. You can actually see, let me grab my laser pointer, you can see the weld mark right here. Okay. Now here we can see a standard cooler fan attachment. We can see that we're connecting 3 out of the 4 pins on this particular connector. We see it says JC Fan 1, if you can read that upside down. So that is a mini Molex or Berg connector that is going to provide that connectivity. I have seen some that are 2 connectors in one. They're each going to be 2 pins, which is literally just a positive and a negative lead. Excuse me. And then that will allow you to connect 2 fans to the same connector. I've also seen some that are very extensive, like a PCI X1 slot, and it will have several pin connectors on the edges, which will then allow you to connect several fans at once. As I said, my machine can easily hold 7, possibly 8 fans. I think there's actually a fan that's on the side of the drive bay as well to help keep that cool. Now, to prevent overheating, those additional case fans are good, but we have to make sure that they're flowing in the correct direction. Large fans tend to perform better than small fans. They tend to be measured a lot of time in what's called CFM, cubic feet per minute, and it depends on whether or not you're using fans that are insulated, if they have grommets that help to rubberize the corners and keep them from vibrating, or if they have a very strong capacitor that allows them to spin at a higher RPM, that sort of thing. Some graphics cards will come with a fan. Almost all of the new ones do. If you want to see a really interesting cooling system, really aggressive, check out the new 3090 cards from RTX. The majority of the card itself seems to be cooling fans, and that's because there's a lot of voltage and a lot of computational exhaustion that goes on with those particular types of devices, which means that there's a ton of waste heat, even in comparison to a motherboard. If we need to enhance the graphics card's ability to exude its own heat, we can sometimes use what's called a fan card, and these will often be mounted next to a device in order to provide additional airflow. Now, make sure that you're providing a fan card that fits the expansion slot you plan to use and that it doesn't impede anything else that's connected inside of your device. More often than not, fan cards are considered a legacy product now, because if you're going to use a graphics card, hopefully the cooling that it provides on its own is good, and that if you need anything further, you can add case fans or move to liquid cooling, which is definitely a much more aggressive method. There are also what are called RAM coolers that will sometimes clip over a DIMM in order to help radiate heat there. But again, the market has caught up, and now most RAM sticks have their own radiant fin blades on them to help move heat away from the body of the DIMM. The older coolers may have been powered by a SATA or 4-pin Molex connector. So here we can see a Vantech PCI fan card. So you can see that this one has 2 fans. It's a standard PCI interface. The PCI Express ones that you would see would probably be about the same size. There are some that are a little bit more aggressive in terms of their fan output. And they'll maybe be 3 fans long instead of just 2, or maybe they'll use a cluster of smaller fans in order to regulate heat over a potentially hot spot, if you will. If all the heat is centered on the back half of the card closest to the I/O shield, maybe there will be 4 smaller fans there that can spin at a higher rate of speed or lower rate to amortize power consumption. I've seen some really interesting configurations for this. The funny thing is that with a standard PCI breadboard, you could theoretically make your own one of these out of standard case fans. You could just actually mount case fans to this card and merge the connectors onto the board. Here's that RAM cooler I was telling you about. This uses a Molex connector, so it's got the blockier 4 pins as opposed to a SATA, which uses the smaller thin 7-pin profile. Now, liquid cooling systems are built on the idea of the same thing that keeps us cool as human beings. Our blood is constantly circulating throughout our bodies. It carries oxygen, it carries fuel for our cells, and it also is a fairly dense fluid, meaning that there's lots of material that can absorb and radiate heat. So that's why, when you're outside on a hot day and you start sweating and your face gets flushed, that's because of vasodilation. Your blood vessels in your face and other easily exposed surface areas of your skin will expand their blood vessels in order to radiate that heat outside of the body, because your core temperature needs to stay about the same all the time. So your cooling system for your computer is very, very similar. There's usually a dissolved salt, something in there that makes it, like a propylene glycol or ethylene glycol in certain cases, in order to suspend more material in the liquid and make it carry more heat, make it better at the what's called transfer specificity. So the pump is going to move this liquid around components, just like your heart pumps blood around your body, and then it comes back to a place where the fans cool the liquid. Then the cooled liquid is recycled back into the pump system and moves across. The hobbyists attempting to overclock processors or RAM or use high-end video cards, really intensive operations, will often use liquid cooling in order to make their efforts more fruitful. So here we see a liquid cooling system courtesy of Thermaltake that exhibits exactly what I'm talking about. Now this case is actually a pretty cool design. It is hydraulically balanced on the top. You can see those actuator arms lifting up the top of the lid, multiple fans mounted there, several fans mounted on the side of the chassis as well as on the back, probably as well on the front. You can see that blue light at the front panel. And the idea with these hydraulic arms is that it's able to balance the doors of opening up the various side panels so that the computer will still sit flat. The base plate is probably very heavy, and it may have counterweights on the opposite side to keep it from tipping over. A thing about this design that I'm not a fan of is the fact that the power supply is up at the very top, makes it very top heavy. Not always a good idea. A lot of the new ones that I've seen are exactly the opposite of this, where there'll be a separate chamber for the power supply at the bottom, isolating it from the motherboard. We can see in the motherboard has these hoses coming off of the big components, usually just the CPU, sometimes graphic cards, things like that. And you can see that the hoses are pretty thick. They have to be, unless you're going to use something like glass, or especially if you're using Pyrex, what's called borosilicate glass. You can then go a little bit thinner. You can see that the tubes go to the components and return back. So there's usually going to be leads that are put on in pairs. They're connected to what are called water blocks, which are these usually plastic. They usually use something like lucite or some other high polycarbonate plastic, high impact, that will contain the liquid. It's then bracketed in place, has a metal membrane that stays in contact with the component being cooled, and allows that membrane to be the point of transference between the cooling fluid and the component itself. The heated fluid is then recirculated back into the reservoir. That's the big black box behind those two orange Thermaltake fans, where it is passed through a series of radiator fins as the cool air from those two big fans blows across it. Kind of like the radiator on your car. If you ever look at your car on the front, you see that it's got that big grill. That's because air has to be drawn in from the front, high pressure air from your car moving forward, that helps to push through the radiator itself. And that coolant is then able to be air cooled by that high compression air. Now, once the coolant has come into the reservoir underneath those fans, what we want to do is make sure that the air bubbles are to a minimum. Air doesn't transmit heat very well. If we look at convection, molecular motion in general, we do better with liquids than with gases, and better with solids than with liquids. So that's why we have the big aluminum block on the heatsink, and that's why we have a very dense fluid, such as antifreeze or something similar, inside of a cooling arterial system like this. Now, selecting a power supply is occasionally a complex process, but there's usually only one of two reasons to go ahead and replace one. If the power supply you have fails or is no longer adequate to support your needs, you'll need to pick a new one. When you're building a new system, of course you're going to need a new power supply. There are sometimes cases that have the power supply already installed, included as part of the price. I would be cautious about this, simply because even though we know the form factor will fit, the power supplies that are included are not usually going to be of the highest quality. You can of course purchase a power supply separate from the case, and then maybe sell off or recycle the one that you've got that comes as the freebie. So if you really like the case, you can get it and then try and figure out something to do to amortize the second power supply, but don't necessarily hang your hopes on these all-in-one packages. They're built to be financially attractive, but not necessarily performance-based. Now, some important considerations. Your form factor is going to determine the power supply size. As you guys will see in your Chapter 4 lab, if you haven't done so already, it's difficult to find power supplies over a certain wattage based on their form factor. So that can be a very limiting issue. If you're trying to build a really small form factor PC, you're going to have an upper limit, at least for most cases, of how much power you can actually emphasize in that particular unit. The wattage ratings, of course, are going to be what allow you to run certain components. That's going to be listed in your documentation. And we want to make sure that we're following the 30% rule whenever we're calculating wattage for a system versus its component load. The number and type of connectors available. Of course, with most connectors, we can use splitters and adapters and things like that to change that around, but you shouldn't plan on adapters first go. You should make sure that the connectors are there if at all possible. That's why I really like, like EPS modular systems that allow you to connect only the cables that you need in order to get your system up and running. It tends to make cable management easier, as well as ensuring that if you need maybe a larger number of SATA connectors for hard drives, you can do that and maybe ignore some of the other supplemental connectors. The number of fans inside the power supply, of course, as with anything else, it generates heat, especially because it's going to be storing that wattage as it brings it in from the wall. So you're going to make sure that the fans inside the power supply are able to keep it relatively cool. Sometimes there'll be some on the front side of the power supply, sometimes they'll be on the bottom, sometimes there will be both. I do tend to like ones that have both because that facilitates maximum airflow. Dual voltage options, if we wanted to operate outside of the US, we want to make sure that we can support both 120 locally and 220 internationally. The warranty and overall quality of the device, we want to make sure that we have some form of support, at least for the first year that we have the device, and then the overall quality will allow it to have a lifespan beyond, a couple of months. I've had power supplies that have lasted me for the better part of 5 or 6 years. I haven't had to replace one in a good while, so maybe I'm jinxing myself here, but knock wood, all will continue to go well because I made a good choice when I bought the one I'm using. So if we want to explain what these wattage ratings mean and how to identify them, usually we need to use these different label metrics, if you will. So let's take a look at what we have here. This is from Sente.com. If we take a look at the AC input at the top, it says 115 over 230, 10 over 5 amps, 50 or 60 hertz. So these are the operational parameters that it can use. That's the AC input. The DC output, what we would expect to see, maximum load of 525 watts. So we can see the big 525 in the model number, we can see the big 525 on the sticker, and we can see that it's also declared under the words maximum load. The 5-volt rail, standard 5, runs at 25 amps. The 3.3 also runs at 25 amps, and the two of them together, that's why they're kind of boxed in that group, is a maximum of 150 watts of power altogether. Your 12-volt rail can run at 30 amps in this case, 360 watts total. The negative 12-volt rail only runs at half an amp and can run at 6 watts. And then we have what's called the plus 5 VSB, 2 amps at 10 watts. So we would need to look at each particular component that we have in our list and say, okay, is this going to require a 12-volt connector? Is this going to need a negative 12? Is this going to need a plus or minus 5, 3.3? I don't really require you guys to worry about the minus 12 or 5 VSB because they're not predominant connectors for a lot of components. They're usually internal only, maybe for the CPU, auxiliary power connector, and what have you. The 5, the 3.3, and the plus 12 tend to be the ones you look at more so for your additional components, for your drives, for your graphics cards, etc. So here we have a breakdown of what those different voltages go to. Your 5-volt tends to be used for just about everything, as does the 12. The SATA connector and the 24-pin P1 tend to be where you see your 3.3. Now your 24-pin P1 is your primary connector to the motherboard. Molex is an older power connector for some SATA drives as well as all of your older IDEs. And then SATA has its own power connector that goes to the various drives as well. Now, when we're determining wattage capacity for a device, we need to consider all of the components inside the case, including things like USB devices that might draw power from ports connected to the motherboard. We also need to keep in mind that there are certain items that draw a lot of power. Your motherboard itself, with the RAM, CPU, keyboard, mouse, etc., is going to draw about 200 to 300 watts on average. Video cards can sometimes get up that far on their own, or if you have multiple graphics cards in Crossfire or SLI configuration, those can also pull a pretty substantial amount of wattage. Your power supply should be rated 30% higher than your expected needs. So add up your requirements and add 30%. Now, why do we do this? Because whenever we're dealing with a power supply, we want to think about it like we do a system that is possibly going to be running at red line all the time. If you were constantly running your car at the top of the gear, absolutely jackrabbiting out of every single stoplight, not only would you likely be much more likely to get in an accident, but you would also possibly damage your vehicle because it's not constantly meant to be run at maximum capacity all the time. Nothing mechanical ever is. Tolerances have to be built in order to give you a butter zone in which they operate best. So that 30% allows us to say, if we upgrade, if we have a surge in performance, if we are heavily working on something, we need to make sure that they're not going to essentially burn out the power supply or cause it to crash, have what's called a brownout or a sag. So that power supply is also going to last a lot longer because we're not running it at maximum capacity. We're going to extend that lifespan. 30% rule, very, very critical aspect of calculating wattage capacity. So just for an example, let's take a look at these tables here that tell us some of the different items that we may come across. As I said, your core system includes your processor, your motherboard, your memory, your keyboard, and your mouse. It's about 200 to 300 watts. Fans tend to be pretty minor, about 5 watts. Your drives tend to be about 15 to 30 watts, depending on whether or not it's a hard drive or an optical drive. PCI and PCI Express have different requirements. Of course, PCI Express has different ranks. X1, X4, X16, etc. Those different iterations are all going to have different power mode requirements, or they may negatively affect the ability of multiple slots to run in a particular mode at the same time. If you look in your documentation for your motherboard, it may say that you have 2 X16 slots, but if you have an X16 slot that only operates as X16 by itself and when engaged will have the other one operating at X8, then that may be a limitation. So just be aware of checking your documentation first to make sure it always supports the functionality that you intend, not just the wattage. Power supplies aside, let's look at how we troubleshoot hardware. This is a critical step in our evolution as technicians, and we need to look at how to be able to handle any problem regardless of the specifics of it. We need to have a general plan. So this is a pretty general approach to problem solving. It's a nice little flow chart. So let's just start from the top and work our way down. Step 1 is to interview the user and back up data. We're going to go ahead and talk to the user about what's going on. We're going to back up data as needed. And once we have arrived at some form of theory, we will go ahead and say, all right, let's examine the system, let's ask some more questions, and we're going to use our best guess to figure out where we are in terms of what's likely causing the problem. Computer won't turn on. All right, let's make sure the cabling's good. Let's make sure all the switches are flipped in the correct direction. Just try unplugging it, plugging it back in. It seems crazy, but one of the most stereotypical responses that we hear, if you try turning it off and back on again, really does work. So step 3 is testing that theory. We're going to go ahead and check and see if our guess might be right. If it is, that's great. We can move forward to step 4. If not, we have to move over into a different step. Are we going to give up? No. That means we loop back to step 2 and come back again. If it is beyond our capabilities, and this is an important thing to know about yourself as a technician, know where your line is, then we go ahead and escalate to another technician who may have a greater understanding of the materials, and then our involvement stops. But that doesn't mean that we don't log our documentation and things like that and proceed from there. When we work in a hierarchical system like this, to where we have, tech support level 1, level 2, level 3, etc., the documentation and the chain of evidence, if you will, is still important. So if we get down to step 4, we made a guess, turns out to be right, great. Let's go ahead and plan our steps to fix the problem, fix it. So that's going to be plan and resolve. And then step 5 is to verify and prevent. Verification of the fix. Is everything good? Yes, then we move down. If not, we have to move all the way back to step 2 and start over again. If we make a theory, make a guess, and it seems to work, and then we fix it and it doesn't work, obviously our theory was either incomplete or incorrect. So we need to make sure we're addressing that correctly. If we did solve the problem and it worked well, could this problem have been prevented? If yes, let's go ahead and take some preventative action. Let's talk to our client. Let's go ahead and write some things down and make sure that in the event of a potential problem in future that has a similar origin, we can possibly avoid it happening. If the drive is slow because nobody runs defragmentation, let's go ahead and put defrag into play. If it's a lack of antivirus scans, if it's a lack of updates, things like that, let's go ahead and make sure that we communicate that these types of things are preventable and can save a lot of time, energy, and in our case, as tech support technicians, money. Now we move to step 6. Let's go ahead and document our findings, actions, and outcomes, which we should be doing throughout the entire process, but this is more of a wrap-up. In certain cases, we can provide a copy to our client, just kind of letting them know, hey, this is what we did, this is what we found, this is the result. In future, this is what we should do to avoid this problem, blah, 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 and then that's it. So, this is definitely a 2 or 3 minute conversation that we've had here, but it walks you through the steps from meeting the user to riddling out what's wrong, to fixing it, testing it, and documenting. So this 6-step process, depending on who you talk to, it may be 7 steps, can do a pretty significant amount of damage to any technical problem to go ahead and whittle it down to something more digestible. The thing I do not recommend that you do is try and fix everything at once. You want to take it one step at a time so that you don't miss anything. It's a critical error that a lot of people make when they're early in their tech support careers. So these are going to be some textual examples of things that we've already talked about. Again, that 6-step system. So again, just to reiterate, interview, backup data, step 1. Examine, analyze, and make an initial theory, step 2. Test your theory, step 3. Plan the fix and implement, step 4. Verify the fix, do preventatives if you can, step 5. And then document and do the wrap-up, step 6. So we've got some resources, of course. We've got the web. The internet is a great tool. The problem is anybody can say anything on the internet. That means that the veracity of what you're looking at might occasionally be questionable. So we want to be careful of just taking the first answer that seems legitimate. We want to use these as leads. We want to use these as, idea starters. This is a place to start looking. Again, if we break things down step by step, even bad advice might lead us to the answer. Now, that's not to say that bad advice is necessarily a good thing, but again, it's getting your mind working. It's thinking about the problem at a step-by-step basis. We also have chat forums. We've got direct chat with technical advisors. We've got technical support email staff, things like that. We may also have built-in diagnostic software we can use, things like PC Doctor. Dell has their own system monitor, things like that. I think a couple of different companies have that. User manuals, service manuals, and then last but not least, technical associates in your organization. Something that's important to know is that experience is probably one of the best resources you can deal with. Somebody who's actually gone in and handled problem A, B, or C will make it so much easier than you trying to dig through pages and pages of stuff on the internet, in a book, in an email, whatever else. It's really easy to forward somebody a PDF and say, well, you can take a look here if you want, but it doesn't give you anything concrete. Somebody who's actually handled it may be able to say, oh, I recognize the step you're at. This is what I would do next, or this is what I would attempt. And I do it all the time. Even as someone who has worked with computers for 30 years, someone who has worked in academics with technical support staff and things like that for the last 5, I still run into issues, or occasionally, I'll pop across the hall and talk to Mr. Sukera or Mr. Vandergriff or any of the other instructors here, and say, hey, this is what I'm running into. Sound familiar? Any advice? And sometimes it's even just confirming what you already thought was the case. I'm not big on confirmation bias, but sometimes that's what you have to do. So there are also, besides the 6 steps, 13 troubleshooting rules. It's not a it's kind of an unwieldy list, but it is occasionally what we have to use to make sure we're not skipping steps. Rule number 1 is to approach the problem systematically. Rule number 2 is to establish priorities. Rule 3 is to beware of user error, sometimes what we call the Aunt Tilly test. Rule number 4, keep your cool. Don't rush. Making sure that you're paying attention to details is critical. Rule 5, make no assumptions. That is a definite challenge, especially for people who've been technicians for a long time. Rule number 6, try the simple things first. Rule 7, become a researcher. Rule 8, divide and conquer. Rule 9, write things down. Rule 10, don't assume the worst. Rule 11, reboot and start over. Rule 12, least invasive solutions first. And Rule 13, know your starting point. That is one that I have to reemphasize for people quite a bit, even people who have been in the industry for a while, because you don't want to try and reinvent the wheel when you're doing troubleshooting. These rules help to reinforce the idea that we're trying to fix a problem. We're not trying to completely rebuild a system. So when we're interviewing the user, backing up data, these are some good questions to use. When you're interviewing a user, we want to look at the difference between an open-ended question and a closed-ended question. Can you describe a problem? What error messages, unusual displays, or failures did you see? When did the problem start? What was the situation when the problem occurred? What programs or software are you using? Then you see down here, has there been any hardware, software, or configuration changes? That is a yes or no question. So that's what we call close-ended, meaning that they can give you a one-word answer, and that is a legitimate answer to that question. On the other hand, if we say, what hardware, software, or configuration changes have there been, then they obviously could say, there haven't been any that I'm aware of, or they could get kind of descriptive with you about it. Troubleshooting like this can be kind of difficult, especially if you're working with somebody who has an affinity with technology. We want to avoid trying to use jargon or other technical speech if we can, try and keep it simple, simply because sometimes the burden of knowledge can be heavy and people can try and make leaps in terms of deduction with incomplete information. So you want to treat every customer as if whatever they tell you is legitimate, process it, but be careful not to fall into the trap of escalating your speech to be on a more technical level. The last one is probably one of my favorites. Can you show me how to reproduce the problem? When in doubt, just let them show you what's going on. Because if they describe it, they may not be using the right terminology. There may be a step that they think is innocuous or minor that could be absolutely critical to what we're doing. As you talk with the user, keep in mind that we need to establish priorities, beware of user error, and keep your cool and don't rush. Don't treat your clients like they're stupid, but bear in mind that it's very easy to make a mistake and not necessarily be aware that the mistake was made. So make sure that before we get started with anything more intensive than just a little observation, back up anything that has not been currently backed up, just in case the system completely dies on you while you're digging around. Rules 5 and 6 help you as you start solving the problem. Again, making no assumptions. We don't want to try and get ahead of ourselves in terms of problem solving. We don't want to eliminate possibilities before we have the evidence to do so. And again, we want to escalate slowly and try the simple stuff first. Reproduce the problem, observe for yourself what the user describes, and try and isolate whether it's a hardware or software-based interaction. Make your best guess as to the source of the problem and question the obvious. Let's look at, is it something as simple as caps lock got left on or something similar? Rule number 7, of course, become a researcher. Go in and dig and find different resources that you can use to try and enhance your ability to get through problem solving. As you test your theories, rules 8 through 11 are very helpful. Divide and conquer. We want to take on one piece at a time. We want to write things down. We don't want to skip over steps. Don't assume the worst. Let's start simple and work our way up. Assuming the worst tends to make you, kind of short circuit your own process. It makes you quit before you have to. And then rule 11, when in doubt, you've got everything backed up, reboot and start over. Now, sometimes when you're testing your theory, it's helpful to have an idea of how to isolate things from being hardware, software, etc. So this is a useful flowchart that we have pulled from the text in Figure 416 to help us with the troubleshooting startup. So the first question is, does the PC boot to Windows with no errors? To the desktop specifically, meaning you can log in. If that's the case, then that means that problems after the boot are not necessarily what we're dealing with. So we're going to cover a different flowchart at another point. If it doesn't, we need to make sure that any important data has been backed up. If it hasn't, we need to go ahead and hook up the hard drive by some other means to recover and back it up. If it is backed up, we need to identify whether or not we have a blank screen. If we have a blank screen, then that means that the display isn't running or something isn't booting beyond the point where the firmware would be producing an image. Do we hear a spinning drive? Do we see lights? Do we hear fans? If no, let's troubleshoot the electrical system. If yes, we need to listen to see whether or not we have a single beep, which indicates that we have the post sequence completing successfully. If we do have that single beep, that means the problem is caused by video, most likely. If not, then we need to go in to start troubleshooting the post code, most likely the motherboard, processor, and RAM. Now, we need to be careful about this because for certain machines, we may actually have a problem where somebody has disconnected the speaker that would provide the postcode beep. Now let's scroll back to if the screen is not blank. So we'll bump up about 3 steps. If the screen is not blank and it shows something, do we understand the error message or other display on screen? If not, then we jump to troubleshooting the motherboard, processor, and RAM. If we do understand the error message on screen, we need to check to see if post is completed and if it's currently trying to load a boot device. If it is, then we need to check to see which boot devices it's trying to process. If not, then we troubleshoot the motherboard, processor, and RAM. If it's trying to find something other than the hard drive, we need to change the boot priority and make sure it's booting to the correct item. So for modern Windows installations, this may mean doing a forced boot to the Windows Boot Manager. If it's to a flash drive or something similar, if it's a network boot, that is going to be contingent on whether or not we get the result we're looking for. If we're not trying to boot something other than the hard drive, we need to examine what the error message tells us about the boot device. If it says that there is a boot device present, then we probably have an issue with the hard drive. If it says that it can't find a boot device, then that means that there's probably an issue with Windows. So the error message is going to tell us whether or not we can find what we're looking for. If it says there's no boot device, then we go ahead and say, all right, let's see if the operating system is having an issue. That's outside of standard boot. That's going to be testing the Windows installation. So here we see a pair of what we call BSODs, or blue screen of death. And what we're noticing is that there's a lot of information that's in here, and it makes your eyes kind of cross because it's a lot of text. But what we're looking for are the actual errors and the technical information thereof. So if we're looking at the first error piece, we see kernel data in page error. That's on the left-hand side. If we scroll down a little farther, we see the stop code information, 0x7a, and then in parenthesis we see 0xC07F16EO, blah, 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 blah. Those are memory addresses that indicate where the particular issue faulted, where the particular failure occurred. If we look on the right-hand side, we see that there's actually a file rather than a problem being detected non-specifically. So we can see here spcmdcon.sys. So we can actually take a look at what is caused by that particular file, and it says page fault in non-paged area. So if we were to just go into the Microsoft website or even a normal search engine and type in spcmdcon.sys and then the error page fault in non-paged area, we could probably find some documentation about that. We also have the technical information down there at the bottom, as you see, as well as where it says spcmdcon.sys, address FBFE7617, base at, and it gives a date stamp. So it's just some technical information about the state of the file when the crash occurred. Some of this information will actually be kind of obscured in more modern blue screen of deaths, anything for Windows 10. It'll usually have a QR code, and it'll tell you some information about the crash there as well. Whatever technical information you can find, go ahead and write it down, or if you have your smartphone or other device, take a quick snapshot of the screen just to be able to re-examine it so you can make sure what error is coming up. The really scary thing is when you start dealing with theory testing and the blue screen information keeps changing. There are different files that are causing problems. That can mean faults due to overheating, RAM issues, possibly malware or other not necessary software is being installed. Here we can see some voltages being identified by the hardware monitor. This is a post message, usually using a UEFI-based system that would indicate some problems with disk read. So we can see here it says disk read error occurred just below the restart. Here are some examples of some different post codes that you might experience, and you'll notice that some of them say Award BIOS as well as Intel BIOS. Award is the same company that does like Phoenix Labs or not Phoenix Labs, Phoenix BIOS. It's the AMD stuff you traditionally see. Intel BIOS is going to be obviously the Intel processor. If you see it just specifying Intel, it may mean that there is a similar code on Award, or it may not. The thing that it points out is the one long, two short includes also that there is no video adapter as well as bad video memory instead of just a non-specific video problem. And you'll notice that continuous short beeps for Award means a memory error, whereas in Intel it means that there's something that's shorting out. It's a loose card or a loose cable. Now, when we're doing step 4 and we're planning our solution, we need to keep rules 12 and 13 in mind. Least invasive solutions first, and know your starting point. So always consider the following when dealing with putting your solution together and fixing the problem. Have a couple of different options present and select the one that's least invasive. It's always easier to escalate than de-escalate. Before we apply the solution, let's go ahead and determine what works and what doesn't in our system, meaning was the system working and it's a minor issue before we get started, or is it like the system will not boot? We need to know what it is we're fixing so that way we're not fixing something that's not broken. And then of course fix the problem. After we fix the problem, we'll go ahead and do a full boot. So that's going to be a full power shutdown, not a restart, but a full cold boot where we actually shut down the machine, it goes dark, you can unplug it, whatever, and then plug it back in. Get it started and see if you can do the following. Can you use peripherals? Can you reach the internet? Can you use Microsoft Office? Does administrative permissions work? Does it work for more than 4 or 5 minutes before it shuts down? If possible, have the user go through some of their usual routines and make sure everything's good. After verifying everything, we should of course ask, could this have been prevented? Now, step 6, documenting what happened, should be something that you're doing throughout the entirety of your process, making sure that you're not redoing steps or skipping over steps that might otherwise help you to identify a potential problem. Good documentation helps you take what you've learned into your next troubleshooting situation, train others, develop effective preventative maintenance plans, satisfy audits, that's a big one, or satisfying queries about your work by either customers or employees. It gives you a knowledge bank to pull back from so that way you can say, without having to tap into memory, you actually have documentation that says, on such and such date, we did this task, this was the result, this is the roundup that we gave to the customer to say, hey, this is what we did. And it helps to justify your hourly rate, making sure that people don't think that you're overcharging or that you're falsely advertising services you don't actually provide. Be sure to include the initial symptoms, how it all started, the source of the problem as identified when it finally does get fixed, what steps you put into place to troubleshoot, and what you ultimately did to fix the problem. So we should have the troubleshooting steps regardless. The initial problem should always be there, but the source of the problem and the ultimate fix should be very closely related. Now let's talk about troubleshooting something specific, the electrical system. Use your senses. If you don't see anything, you don't hear anything, if you smell something weird, that's not a good sign. If the computer locks up or gives you error codes, shuts down unexpectedly, or if you hear the power supply whining and the system can't get up and running, that can be a sign of a power supply that is too weak to run the system in the configuration that it needs, especially if you've just added a new component such as a graphics card. Questions to ask, of course. If you smell anything burnt, don't try and turn the system on. Let's go ahead and replace that fried component first. If we hear a whine, it may not necessarily be that the system is too weak. It may also be that there's a short. Again, check your simple stuff first. Is it plugged in? Is the power outlet controlled by a wall switch? That's something you run into in apartments from the 80s a lot. Instead of having to put in overhead lighting, they would instead have a light switch that was connected to the opposite side of the room, so you could put on a standing floor lamp. Are any cable connections loose? Is there a power strip with the protection switch turned off? Is the circuit breaker blown? Has the system overheated? Are there EMI sources that are possibly causing issues? The EMI stuff is a little bit older, but it is still a good thing to check. You never know what that kind of interference might be doing to data corruption or what have you. Now, if you need to take a look inside the computer case, we always want to follow our standard disassembly procedure. Turn off the computer, unplug it, discharge it, and open the case while remaining grounded. So either keeping your hand in contact with live metal or wearing an anti-static strap, which tends to be a much better idea. Of course, check all your power connectors, look for burnout parts, look for potential shorts or kind of little scorch marks on the motherboard itself. Look for wires or connectors that seem malformed or damaged. If you suspect the power supply is bad, just whip out a power supply tester and give it a quick check. Sometimes what I've run into is that the power supply is perfectly fine, but when I check one of the connectors for the SATA cables, specifically the one going to the operating system hard drive, that connector has gone bad or has cooked in some capacity. Other symptoms that might indicate an intermittent problem, meaning something that comes and goes. The system hangs for no reason, memory errors, data problems, either incorrectly written data or corruption. The keyboard stops working, the motherboard fails, the power supply overheats, power supply becomes very noisy. To eliminate the electrical system as the source of a problem, let's consider that the supply is inadequate or faulty, and then try and swap it out for one that we know is good, or hook it up to a tester in order to check it. We need to examine these things. What I have done on occasion is taken a power supply out of a system, plug it in, and then try and force it to connect using a tester, and then checking to see what the temperature is while it's running, checking all the connectors, making sure that there's not a bunch of dust or things like that inside. Now let's look at some motherboard issues that might come up. Of course, we talked about standoffs and spacers, making sure things were keeping shorts from occurring between the motherboard and the chassis. Take a look at that. Make sure that all of your standoffs are nice and tight, especially if you're switching out your motherboard. Make sure that when you're unscrewing things, you're not also unscrewing the standoffs on accident. Shorts in the circuits on the motherboard could also cause problems. Make sure that if there's something that happens on the underside, that you're able to identify it. You may also want to check and make sure there's not loose components that get trapped underneath the motherboard against the chassis, which could cause a short. Overheating, of course, there's a ton of different signs of overheating. Blue screen, visibly, hot to the touch. You can see that there's sometimes like a little bit of a heat ripple that comes off. That's really, really hot. You can see the fan, especially if it's in a cooler room. You can touch it, things like that. Sometimes you'll smell that kind of hot, burnt dust smell. Not necessarily that something got scorched, but just kind of that, you haven't turned on your heater all winter, and then here it comes, and now everything smells slightly toasted. If you suspect overheating, of course, you can check the software-based temperature monitors. There are also external sensors that you can buy that you can clip into your case that can trigger an audible or visible alarm. Of course, keeping things clean is probably the easiest way to go about it. Using a blower, compressed air, anti-static vacuum, that sort of thing. Check airflow inside of your case to see if your fans are running. Install extras if you can. Chassis air guides are not bad ideas. Those will guide air directly to your processor, being that that's usually the hottest component. Sometimes, of course, high-end graphic cards and power supplies can go a little hotter. It just depends, but CAGs are always helpful. I think Intel and AMD both recommend them. Make sure that your faceplates are clipped in place correctly, that you don't have things just sitting open. That makes it very difficult to get enough back pressure with your fans to force the airflow necessary to get a very high rate of air movement, cool everything down efficiently. Excuse me. Also make sure that there's not cables in the way. You don't want things just kind of hanging that could block the fan and cause it to lock or stop. You also don't want a cable to accidentally become damaged by impact with another object. So here we can see a cooler fan that's dusted over. That can cause those bearings to fail and the processor to overheat. We could of course have kind of a scraping or rattling noise from debris that gets caught in between the fan and the heatsink. Here we can see someone installing an extra exhaust fan. Here we can see that their power supply has a what we'll call a front-facing fan. It faces towards the front of the case rather than there being one underneath. I prefer the ones that have both, but you know, if you have to make a choice, I like the ones that are on the front. It tends to be a little bit better at keeping airflow moving in the direction that we would want. Make sure that the case is not butted up against something that's going to cause it to just soak heat. So a lot of people I've seen have desks that have a little cabinet below that you can put the tower in. If you do that, make sure the tower is not resting against one of the side walls. I mean, obviously it has to sit on the floor of the cabinet. It's not going to float. But you want to make sure that there's enough room on either side of the case, top and sides, to make sure that the airflow can actually move around. You don't want it all to be trapped. Make sure the cooler is correctly secured to the processor. If the system is failing due to overheating, let's go ahead and unplug the system and leave it off for about 30 minutes. What I will usually do in that case is go ahead and take off the side panels, go ahead and take out my, my compressed air or my anti-static vacuum, make sure everything is nice and clean, check my cable management, and just let it sit and air out for half an hour. You know, unplugged, completely unplugged. Check and see if too many peripherals have been installed inside the case. This is something I run into with people who have enough technical knowledge to know how to add a card, but they don't understand that there's a point at which you should probably look at upgrading the machine or changing out the devices that you're using for maybe using a USB based option instead of just using an internal card. You can always check to see if the firmware has an update available. That is one of the situations under which we would perform that update if something is obviously crashing. Check to see if your thermal compound is hardened. You know, if you feel like, you know, if you see like powdery residue or things like that around your CPU, it could be that the thermal compound is completely dried out and is crumbling. That's allowing air pockets to form and allowing heat dissipation to get kind of bunged up between the heatsink and the CPU. Also consider whether your case design allows for good airflow. So here are two diagrams showing us what we consider to be good airflow and poor airflow. So let me go ahead and grab my highlighter real quick. And I'm going to do this kind of a dark blue. So from the front vents we see here, we've got airflow coming in. We've got movement going to the processor unit here. Let's assume that we have a fan that is allowing us good circulation at this point. We have a standard exhaust fan moving towards the back of the machine as well as into the power supply and out again. In this case here, they also have a front-facing airflow on the front of the power supply, so that will allow better airflow movement. If we have a graphics card, that's probably going to have airflow moving upwards from the bottom of the case, which is what we want to see. We want heat to rise and to move towards the back of the case. So again, we want to do front to back, bottom to top, so that way we can draw heat away. The airflow should also be able to catch the drive bays, just so that way it's not sitting here stagnant. We want airflow to be moving between. And again, if we assume that all of the case panels and openings are sealed up, these are the only ingress and exit points, ingress and egress points. So air only comes in here, only comes out here. That's able to prioritize how that airflow is processed. Over here, let me switch to red because this is supposed to be bad. Front of the case doesn't have a fan, so that means there's a lot of air that's just sitting right around here, and then the drive bays as well. That is accumulating a lot of heat, and it's very, very stagnant. Now, if we have side vents, I assume they don't mean that they're on the bottom. They probably mean that they're over the side of where the case is. That's, if you look at your case, you'll probably see a grill on that side. There's also a rear of the case access that doesn't seem to have any fans, so there's no access here. Again, stagnation. The processor doesn't seem to be pulling enough air to be able to move it to get it nice and cool. And then we have the airflow going out through the power supply at the back. Now again, we only have air that seemingly is coming in from these side vents and moving outwards, so the front of the computer up here is entirely stagnant. There's no airflow. So that is considered to be very poor design. So use a power supply that has vents on the bottom and front, as I said. Intake fans are great, extra fans are always good. The CAG, which we brought up a little bit ago, I'll give you a bit more of an explanation of what that is. It is an air duct that helps to pull air directly from the outside and onto the cooler and processor. This is what the CAG actually looks like. So you'll see that it has 4 mounting points, kind of like a standard fan would, and then it has this telescoping thread. So this little ridged area means that it can be slotted up or down to extend to the correct height, and the 4 corners are supposed to sit over the edges of the cooler that your processor currently uses. So this is just a nice uninterrupted channel to pull air directly from outside. Here we can see, again, one of my favorite processor assistants there, the power supply with the front and bottom vents, and an exhaust fan as well. Great choice. And here we can see the chassis air guide locked in place. Hopefully it doesn't show us the great side-on view, so we can't see where the processor is, but that's where we should see it line up to the CPU. Now this is in a retracted form. It will be able to extend to be able to connect. Now, laptops are a little bit different. We have to be aware that, of course, we don't have a power supply per se, but we do have a battery pack. These are traditionally lithium-ion packages in either 6 or 9 cell iterations. I have seen some variants between that, but 6 and 9 tend to be the most common. They also use an auto switching feature in the AC adapter, which allows them to move directly from 110 to 220, provided they have the correct connector. So they'll usually have some resistors inside to detect which voltage is coming in and switch accordingly. The good thing about a laptop is that you can usually keep an extra battery on hand pretty inexpensively. The thing is that you have to charge it, so you will have to swap it out on occasion. If the power is not getting through to the system, or the battery indicator light is lit, that it's got a low charge, let's go ahead and verify all of the connections. So we have the plug at the wall, where the AC adapter plugs in. We have the transformer block, which usually has a separatable piece there. We have the cable that goes from the transformer block to the laptop itself, and then we have the internal connections. So we're going to start from, of course, least invasive. Let's make sure that the wall socket is good. Let's make sure the transformer is giving us a green light. Let's make sure there's no damage to the cables, and that the AC adapter is snugly connecting into the laptop itself. If we have to go inside, obviously it's going to be a little bit different. Something we want to be aware of is that there is a hinge right there where the screen of the laptop, of course, pivots. Sometimes, depending on design or things like that, especially if it gets dropped, the cable that feeds the power controls to the power button on the edge of the laptop can sometimes get caught in that hinge and pinched, or sometimes even severed. So that is something we want to look at. Now we're talking about troubleshooting the core system. If we're seeing issues that the core system is failing, we'll see attempted boots where it tries to start up and then fails, error messages, the system reporting less memory than installed. That's a big one. If you've got 16 gigs of RAM and it shows that you have like 13, that's really weird. Anytime you see something that's not a proper multiple of the powers of 2, so if you saw 12 gigs, that might not be a freak out point because somebody could have 8 gigs in one stick, 4 on the other. But if you saw 17 gigs, that would mean that somebody has like, a 16 gig stick and a 1. That doesn't make a whole lot of sense. So we want to make sure we're double checking those potentially erroneous numbers. And then, of course, if we have a component on the motherboard, one of our onboard ports that stopped working, then we need to check it out. And of course, check the simple stuff first. So let's try and find the source of our problem by, Googling what we know. Let's go ahead and dig around for the error message. Let's do a virus scan. Let's go ahead and do memory diagnostics if we have a system that supports it. Let's check Device Manager. Let's check Event Viewer. There's a lot of utilities inside Windows that can help us to identify potential problems. We can also check through Windows updates or patches, make sure there's not something new that is being missed, what we call a 0-day. If the problem began after a new change, let's go ahead and uninstall whatever that was or find a way to disable it. Use the system window to find out how much RAM you have. If your RAM is too low, then yeah, you'll start to see some weird events occur, especially after a major patch for your operating system. It may be that a certain feature now requires more RAM and is causing a bit more demand on your system. Using the task manager can help you to identify the current performance of your system, and by performing what we consider to be a very light benchmarking and baselining, you can see, okay, under load, this is how my system performs. Under normal circumstances, this is how it performs. And you can get kind of an idea based on that, a little bit of ballparking. You can also check your firmware to make sure all of your settings are good, turn off any quick booting features. As we talk about, quick boot skips over a lot of non-vital error checking, so it can lead to problems down the road that could have been prevented. Let's go ahead and check and make sure that the board's firmware is good. So if we're going into UEFI, let's make sure that all that firmware is good. Check your manufacturer website for diagnostic software. Again, this is going to be manufacturer of your motherboard, not of your CPU or of your RAM. Make sure all of your drivers are updated. If you're having problems with a port, you can test it out in a couple of ways. What I usually do is see if there's some kind of loopback plug. If you can't fix it, in certain cases you can just turn it off and use an alternative port. Depends on what it is. I have definitely gone in and put in a 4-port USB 3.0 hub because the USB 3.0 port on a motherboard it was given some issues. Turns out it was a driver problem and we fixed it later, but we needed it to work at that point, so we were able to get it kind of up and running. Also, at that point, once we get to the place where we see some major failures and we can't identify them anywhere else, we need to look at the holistic nature of the machine. If we see that the motherboard, processor, and RAM are showing issues, but we can't find the issue, could it be overheating? Could it be the power supply? Could it be the hard drive? Another thing, and this is, I like the fact that this is near the end because it's not very common. You may have a situation where the socket that your CPU sits in is correct. You've got the correct CPU in the correct slot, but the chipset on your motherboard does not support it. Maybe it's too new. Maybe there's a memory option that it conflicts with. Just be aware that that can happen, so that something that does fit normally and plugs in and everything looks good can still give you some errors. Startup repair is a process that is built into Windows. Essentially, if your reboot fails, I think 3 times, it'll automatically try and move what's called ABO, Advanced Boot Options, to try and run startup repair. Now, I will say startup repair can be kind of obnoxious because if you're rebooting a lot because you're trying to test something or things like that, you have to kind of ignore it. If necessary, you can go ahead and change your boot priority in order to run startup repair from an outside source. So instead of trying to use the internal repair processes, you can use a flash drive or an optical disk. You'll go ahead and go into the troubleshoot phase, click on startup repair, and be able to select your options. There's a couple of different ones. You can go into, this is what's called a safe mode, the top 3. Safe mode, standard, safe mode with networking, safe mode with command prompt. The reason that you see those 2 with options is because those 2 things are normally disabled during safe mode. Boot logging, low resolution video. Low res video is great if you're having issues with your graphics card. Last known good configuration, basically the last time the system booted normally. It keeps an idea of what those configurations were. You can also disable driver signature enforcement. Now, this is a malware vulnerability, so you want to make sure that you only do that if you have to. Now, this screen will look a little bit different if you go into Windows 8 or Windows 10. For one thing, it'll probably be blue, but in general, it'll give you a lot of the same options. If we've checked Windows, we've checked firmware, and we can't identify the problem, let's go ahead and take a peek inside, and just like anything else, let's go ahead and escalate slowly. Make sure all of our connections are good, look for physical damage, reduce the system to essentials. So this means take out all of your peripherals, take it down to 1 RAM stick, 1 hard drive, just your boot drive, take out your graphics card, just use the onboard video if you can, that sort of thing. You want to strip it down so that the system can be baselined at, okay, the motherboard does function, or the RAM is reading, and then you start slowly adding things back. You can use a post-diagnostic tool. Sometimes there'll be a PCI card or USB. Suspect the problem is caused by a failing power supply. Swap out the processor, swap out the motherboard. At that point, you're getting pretty deep if you're swapping out main components like that, but it will sometimes be necessary. Before you change out the motherboard, though, you want to make sure that you have checked the voltage output of the power supply, because, and I had this happen to a car of all things, I had my alternator essentially cooking my battery on accident. It was just my mechanic had, I guess, connected a wire that he shouldn't or something similar. It can happen with a power supply as well, to where it can accidentally be pumping too much voltage into an area and damaging the motherboard. So you don't want to have the same thing happen twice. Here's our chapter summary, of course. I'm not going to read it to you. I'll let you guys read it, so I'll give you about 5 to 10 seconds per slide. Okay. So if you have any questions further than what we talked about here, of course, you can check your text. You can always hop onto Google or YouTube. Just over an hour today. So hopefully this was informative, gave you some things that will hopefully jog your memory the next time you're staring down a machine that doesn't want to behave. If you have any concerns or questions, as per usual, you can email me at jearmke063@cfcc.edu, or of course you can contact me at my Google Voice number, which is 239-7814. Hopefully I'll talk to you guys again real soon, and I'll catch you next class.